the meaning of the topic is still the same, monetizing Indian coal, but I try to give it a more meaningful title here. So, using coal gasification to achieve energy self-reliance and still addressing the carbon emissions. So, along with me, my co-authors Nankishore, Soumya, and Kakul, they have helped me to put together this presentation, though they are not physically present, but they have played a role in helping me this presentation. So agenda here looks quite long, but I'll try to complete within 15 minutes. So briefly about the coal situation in India, what gasification is, what various product slates we can make from gasification, then how does the gasification emission compare with the traditional coal-fired power plants, which is majority of Indian coal uses currently, in fact, across the world. And then a little bit comparison about the global warming potential of various greenhouse gases. I'll try to put that in the context here. Then the burning issue of CO2 utilization. Coal is still the coal, and it's a carbon-rich feedstock, so it's still going to produce a lot of CO2. So I have put together some of the alternates, how we can make use of the byproduct CO2. Then other synergies with the ongoing development in the energy transition, which is green hydrogen, how coal gasification can be synergized with that. Then a little bit about Fluor gasification experience, and then conclusions. So coal scenario in India, I think this is a very well-known fact that India is fourth largest coal reserve in the world, about 350 billion metric tons. So we are at the same time the largest consumer as well as the second largest producer of the coal in the world. So what is the drawback? So majority of Indian coal is low grade with very high ash content, and presence of fluorides makes it very difficult to deal with. And then very high ash fusion temperature, so makes it quite difficult to gasify because you need very high temperatures. Most of the coal, as I said, low grade non-coking coal is used for the power generation using direct fired boilers, which is directly adding all the carbon in the coal in the form of CO2 into atmosphere. But the positive side of it, that coal does not have a direct parity with other fuels such as crude oil or natural gas. It has its own market, which is dependent on its own supply and demand situation. So a little bit about the stats. 70% of coal in India used, in the thermal power plants accounts for close to 50% of CO2 and SOx emissions, about 30% NOx and 15% of PM 2.5. So all the dangerous species. Indian coal fleet emitted 1.1 gigatons of CO2 in 2019, and of course contributed to poor quality and all kind of emissions in the SOx, NOx, and particulate matter, and impacting health, economy, ecology, and economy directly or indirectly. So what is the clean solution? We are sitting on the abundant coal reserves and it's still importing almost 80% of our energy needs through crude oil or the natural gas. So, how with the emerging concerns over the CO2 emissions and other pollutants such as NOx, how do we use this abundant coal in a cleaner way? And I believe the potential cleaner solution is the gasification. So gasification is basically the reaction of the feedstock with oxygen and steam at high temperature. And primary gasification reactions, the aim of the gasification is to produce carbon monoxide and hydrogen. But In addition to that, there are some side reactions such as the water gas shift reaction and methanation. So they produce CO2 and methane. Conditions typically, 900 to 2000 degrees Celsius. Pressure could be atmospheric to about 80 bar gas. So in addition to the main hydrogen and CO, which is called synthesis gas, in the coal gasification process, there are, the nitrogen present in the coal, as well as the nitrogen that comes with oxygen is converted into nitrogen, ammonia, or HCN, depending on the gasifier operating conditions. Sulfur converted into H2S, COS, and CS2. And then in addition, as I talked about earlier, there is chloride, fluoride, and then some metals like mercury, arsenic. Those also end up in the syngas. And that those things, need a special attention and need to be, the design needs to take care of those. Otherwise, they can create a lot of problems in the downstream processes. So we've got a syngas cleanup, acid gas removal steps, and then the end product, depending on what it is. If it is syngas, it could be direct combustion, using IGCC route to make power, or syngas to make other products. Sulfur gives an opportunity, in this case, to be captured in the form of sulfur as elemental sulfur or sulfuric acid, as opposed to SOx in case of the boilers. So feedstocks gasification is very versatile and can take wide variety of feedstocks, including high-S Indian coal, petcoke, other refinery residues, such as vacuum bottoms, asphaltenes, acid-soluble oils, and also the various biomass, such as municipal waste, woody biomass, agricultural waste, industrial hazardous wastes, and even the medical wastes. So it's very important, considering, there are all kind of species present in the feedstock. So it's very important to understand the feedstock, to pick up the right technology, to pick up the right syngas cleanup steps, to pick up the right gasification overall plant configuration. So some of the key parameters are the heating value, which is LHV, the moisture content of the coal, then ash content, ash composition, that basically determines your, what is going to be the composition of the bottom ash or the slag from the gasifier, and what's going to be the split of some of the ash components, and some of the ash components get carried over in the syngas. Then the melting temperatures, and most important, I think, generally ignored if you're not experienced enough, these trace components, which are maybe in ppv levels but very dangerous to deal with. So you need to pay special attention even up to the ppv levels of mercury, arsenic, sodium, potassium, chloride, fluorides, and other halides. And of course, the grinding index, because the hardness is measured in terms of the hard group grindability index or the bond index. So that is important to size your, coal feeding or the coal preparation equipment, I would say. So here is a simplified overview of the key process steps in the gasification process. So we have an air separation unit which provides the pure oxygen, or I would say close to 99.5% or higher purity oxygen for gasification. Then we have the gasification block itself along with heat recovery. Heat recovery is optional depending on the technology. It could be a direct quench or the heat recovery steam generation option. Then the raw syngas that comes out of the gasifier after cooling needs to be scrubbed for any chloride, fluorides, conditioning, I mean, is the shifting essentially, or the COS hydrolysis, depending on what the end use is. And after conditioning, it goes through the acid gas removal step. If there is mercury present, so before acid gas removal, there is a mercury removal dot pad as well. So acid gas removal, it separates sulfur and CO2. Sulfur could be again, sulfur is separated as H2S, which could be further processed to make sulfuric acid, or it could be processed to make elemental sulfur, CO2. So the beauty of this CO2 is this is concentrated, essentially pure CO2. So it does not need to be captured. It just, compress it, and with very mild purification, I would say, you can directly, compress it or inject deep underground, or if there are potential uses nearby, it can be used for other beneficial purposes. I'll cover the potential beneficial uses for CO2 in the subsequent slides. And then clean syngas can be used to make variety of products. So gasification technology options, there are a number of technology options for gasification, and primarily categorized into three main categories: fixed or moving bed, fluidized bed, and entrained bed. Fixed and moving bed, very high residence time. Fluidized bed, somewhere in between. Entrained bed, very less residence time. And as based on the flow profile, you can see the feedstock size becomes finer and finer as we go towards entrained bed from fixed bed. Then oxidant, it could be air or oxygen, depending on what the end use is. While in case of entrained bed, it is mostly oxygen, because you have to heat up the coal to very high temperatures to melt the ash. So if we go with air, in that case, a lot of your energy goes into heating up the nitrogen that comes along with the air. What that means is a lot of additional CO2 generation. Ash handling could be slagging or non-slagging. So fixed bed is slagging and non-slagging, both options. Fluidized bed, non-slagging, and entrained bed is always slagging. And here is a list of commercially available technologies in the market. Okay, so as I said, once you reach to the syngas, you have opened the door for number of products that you can synthesize from syngas, including the direct use of syngas for power and steam, using syngas for direct reduction of iron, as well as syngas can be directly used as oxogas for oxochemical synthesis. It is a source also for hydrogen to the refinery and oil sands projects. Oil sands especially is not applicable in India, but it can still be used as a source for hydrogen for the refineries, such as Reliance is using that. Then all kind of liquid fuels, synthetic natural gas, methanol, and methanol again opens the door for various derivatives that can be made, and fertilizers. Okay, I think so this may be of interest to you. So here I have tried to compare what is the value addition to various products with respect to the cost of coal. So Fluor has come up with a way to simplify things. So we have come up with, okay, $1 per million BTU corresponding to the $1 per ton or $1 per liter prices. So on an energy basis, you can see the value addition. So if I try to summarize this slide, so the message from this is coal to anything that you synthesize, the highest value addition is essentially where you get paid for your carbon, as well as for the oxygen. The moment you go into the rejection process of carbon or the oxygen, your value addition drops. So basically, what I'm trying to say here, make the oxygenated products and the products which are rich in carbon. So you can lock most of your carbon in the coal in the product. That way you help also the environment by locking the carbon, most of the carbon in the coal into the products and reducing CO2 emissions to atmosphere. Okay, so this is a small comparison about how 1 million ton of coal processed in a coal-fired power plant versus same amount of coal processed to produce methanol. So you can see the CO2 emission, there is close to a 30% reduction in CO2 when you process 1 million ton coal to make methanol instead of power. SOx emissions becomes almost nil versus quite significant in coal-fired power plants. Similar is the story with NOx. And for mercury, chlorides, fluorides, particulates, there is essentially no way to capture them in the flue gas, I would say. While in gasification, they are captured in the purification process and they do not pose any environmental hazard. Even the ash content gets reduced quite significantly. Because coal-fired power plant, the carbon conversion is much poorer compared to the gasification plants. And in addition, coal-fired power plant, in this case, I've compared the circulating fluid bed boiler. So there, if the sulfur is high, in that case, you need to use the limestone as well. So that limestone also ends up in the ash. So that's why ash content is very high. Then this slide talks about the greenhouse potential of various gases. So carbon dioxide, when it's measured, it's measured on a scale. It's 1. Methane is 25 times more potent. Nitrogen oxides is 298 times. VOC is 3.112 times, and carbon monoxide 1.57 times. So specifically to mention in this particular case is like coal, so coal emits coal bed methane, even the landfill sites, which are used for dumping the garbage, they emit a lot of methane. So, methane emission is 25 times. So like 1 mole of methane is 25 times is equal to like 25 mole of CO2. And similar is the story with the NOx. So, there are other pollutants also that contribute quite significantly, even though they are emitted in small quantities.
Sunil, can you conclude in next 2 minutes, please?
Okay, sure. So, as I talked about CO2, CO2 is capture ready. So there are various uses. We can use enhanced coal bed methane recovery, enhanced oil recovery. We can use in the beverage and food processing, dry ice. And then and nowadays we have these green hydrogen. So CO2 from the gasification industry can be combined with green hydrogen to make methanol. Similarly, the byproduct nitrogen from ASU can be used to make green ammonia using the green hydrogen, and urea synthesis using the CO2 from gasification. In addition, in the Western countries, especially in the Europe and US, there is something called diesel exhaust fluid, which is used to reduce the NOx emissions from the diesel vehicles. So another use is the greenhouse farming, then algae growth, which can be further used for biodiesel production, then aerosols, dry ice pellets for use, sand blasting, removing some of the paints. And also it can be used to neutralize the alkaline water. So other CO2 reduction options are coal gasification. We can use biomass as a co-feed. Then coal gasification can be integrated with water electrolysis using green power. So we can synthesize green methanol. And if these two concepts are combined, like water electrolysis and gasification, then we can have a very good synergy using the byproduct nitrogen from ASU to synthesize ammonia. And also we can use the oxygen byproduct from electrolysis in the gasification that serves the need for the oxygen without requiring any treatment. So that removes the, get rid of or minimizes the capacity of the ASU. Then here is a list of selected gasification experience. Some of the recent ones you can see, especially in the Western countries, in US, a lot of biomass gasification projects are going on. Even we recently did a blue fertilizers, blue ammonia project for Utah, which is essentially CO2 capture along with ammonia, urea, and ammonium nitrate, various fertilizers. And captured CO2 will be pipelined and used for enhanced oil recovery. So this is a long list of experience. Fluor has been in the gasification industry since 80s, starting from Sasol 2. And we built the world's largest petcoke gasification for Reliance in India. Again, I think you can look at a lot of gasification plants that are still operating. So to sum it up, basically, yes, gasification is complex and quite challenging, but coal is not going to go away from people's lives very easily, because worldwide, if you see, a lot of people are still dependent on coal. So we need to find an alternate clean use for coal. And I believe gasification offers, is a technology that offers that opportunity. The syngas cost of production is more economical compared to the imported LNG in India. Even byproducts of gasification, such as sulfur, nitrogen, argon, sulfuric acid, they can be utilized to generate additional revenue. And more importantly, gasification plays an important role for energy self-reliance in India, with the demand for the products, specifically the chemicals, petrochemicals, and fertilizers. Gasification also addresses the increasing global warming concerns due to CO2 in a much cleaner way compared to the current uses, which is direct fired boilers. And gasification, of course, offers the various blue hydrogen and chemicals, as well as fertilizer synthesis options. It offers a good synergy with electrolysis. So, but what is key for the gasification success is we must use the best technologies and the gasification experience to design engineering companies. And a lot of people have been convinced with that, and they have successfully implemented and taken benefits of the gasification. I think with that, I will summarize.
Okay, thank you.